Let us now introduce, okay, before even introducing, let me address this question, that why I am doing all these things when the course is all about astrophysical fluids, why I mean describing all this passage from one level to the other level of theory. The answer is very clear. If you are interested in the research in astrophysics, or you want to develop a deep insight in the astrophysics, then you have to understand the scope of different levels of theory. Now, tomorrow if you just come across a certain phenomena and then you know the scope of different levels of theory, then just by verifying those conditions, under which condition which theory is appropriate, then you can simply say, well, okay, under this condition, so this is the temperature, this is the density, so quantum description will not be there. Okay. So, you see, by that you can eliminate redundant possibilities. Okay. So, that is very essential. Okay. And also this is very good to develop a global view. Now, let me introduce two very important concepts. One is the concept which is somehow associated with the concept of phase space, one is the concept of gamma space, another is the concept of mu space. Okay. Now, gamma space is, let us take a system of n identical particles, okay, which are behaving classically. Now, if we are just restricting ourselves in 3-dimensional universe, the complete set of the system will then be given by, as you can easily understand, R1, R2 up to Rn, and U1, U2 up to Un, right. So, everyone has 3 components, so it will be having 6n components, right. So, if we now just freeze the time, that means we take a snapshot of the system, okay, then we will see that it will just give us a combination of 6n values, right. Now, this combination is called a state of the n particle system, classical state, okay, or the state in classical mechanics. Now, if you then consider a phase space, let us say, this is just a superficial, artificial drawing, okay. This is not 6n, but let us suppose this is a 6n dimensional space, and one point is just giving you the value of, or the ensemble of these 6n values at a given instant of time. Okay. If this is the case, then the corresponding phase space is called a global phase space or gamma space. So, if we have an n particle system, gamma space basically gives us the description of the global state by a single point if the time is frozen. That means, one snapshot, one point, one snapshot, one point. Okay. Now, let us say, for example, if you have a system having 3 particles. So, you can easily understand that the number of dimension, the dimension of gamma space will be 6 times 3, 18. So, every time you click and you take a snapshot, you will have an ensemble of 18 possible values of R and U's, right, and that will give you a single point of that corresponding gamma space. Now, what is mu space? Mu space is possible only when the system is composed of n identically behaving particles, n identical particles. Okay. Then what happens? Basically, these particles can only be distinguished from one another just by their position and velocity. They have exactly identical physical and chemical properties. They are only differing from each other, okay, by their position and velocity. So, only the mechanical state is different. If this is the case, then only you can say I can actually define another type of phase space, where every single particle state, now say every single particle has how many number of variables to be identified? 3 space coordinates and 3 velocity coordinates, right. So, it will need 6 values, right. So, then we say that in mu space every single particle is giving the description, every single point is giving the description of the state of one single particle. So, in this case where the gamma space is of 6 n dimension, mu space will simply be 6 dimensional, and this is just for one single particle. So, now if I say that what will be the corresponding mapping of this point to this point, to the this point to this phase space, this will be an ensemble of n points, right. So, this is called the mu space or particle specific phase space. Okay. Now, you see, when this particle as a function of time, let us say it evolves like that, then that means the total system basically is evolving along this trajectory. So, I am just studying, I am just taking snapshots with time, and I am seeing that this particle is moving this. Okay. That means what is the meaning of that? That means that with this initial condition the system starts, and then the laws of mechanics compels the system to move having all these subsequent values of r and v. Then if this is just a line over there, okay, a curve over single curve over there, these will not have a simple picture like that, because every one of them is now evolving like something like a path of something like this. Okay. You can see. So, a single trajectory in gamma space will now be an ensemble of n trajectories, okay, or a group of n trajectories in mu space. Okay. Now, till now I have roughly used the ensemble in order to just use the word group. Okay. Ensemble, I just said that a number of or a collection of trajectory or something. Now, there is a formal meaning of ensemble. So, from now onwards when I will use the word ensemble, it will be basically used to designate a specific thing. So, ensemble is a set of many replicas of the same system. For us, the system can be a system with n particles, okay, with n particles. Then ensemble is nothing but a collection of, so if you just remember what gamma space was, okay, the state of the whole system of containing n particles, okay. So, having 6 n values in it, okay, was designated by a single point in gamma space. Okay. Now, let us say at an instant of time we mentally create, or rather imaginarily create, n number of such points. N means small n, okay, another number of such points. What is the meaning of that? Basically, we are creating n number of collection of 6 n values, okay. That means we are creating n number of initial conditions, and we let the system evolve, okay. We let the system evolve. This is we are talking in terms of gamma space. Okay. So, every member of the ensemble will then take a path of evolution. Okay. Okay. Will take a path of evolution. Now, if this number of ensembles, the number of rather ensemble points, okay, are distributed sufficiently densely. So, if the number of ensemble points, so ensemble is the collection of all those points. Okay. If the ensemble points are distributed sufficiently densely, then we can define a density of the ensemble points, density of the ensemble points. In gamma space, okay, and that density is designated by rho ensemble. Okay. So, once again every point is designating one single state, one global state of the system containing capital N particles. And now I am saying that at an instant of time we are imaginarily making n type of small n time small n number of such collection of 6n values. Okay. So, every single entity of the set contains 6n values. So, finally, we have small n number of this 6n value small n number of this type of collection, each of which contains again 6n values. So, this total cluster or this total collection of points, okay, n points is known as ensemble, and a single point of ensemble is known as an ensemble point, and ensemble point is nothing but a possible initial condition. Okay. And then after that we basically let the system evolve according to the trajectory, okay, according to the evolution trajectory. Now, what we claim is that if the ensemble points are distributed sufficiently densely, that means we are creating such an ensemble where we have artificially or imaginarily created a very large number of possible collection of 6n values, collection of points, each of which contains 6n values of r and v. Okay. Then we can define that in gamma space, okay, the ensemble points are very dense. Okay. And then we can define a density of the ensemble points. Look, ensemble point density has nothing to do with the real point density. Ensemble points density is a density which is defined on phase space. This simply says, when we say that the ensemble points are distributed sufficiently densely, that simply means that we have created a sufficiently large number of collection of points where each points are giving a possible state of r and v's. Okay, that is it. Now, this density of these ensemble points is known as, it can be designated as rho ensemble, rho ENS. Okay. Let us now talk about the very fundamental theorem which is known as Louville's theorem. Okay. What is the statement of Louville's theorem? Louville's theorem says, let us say we are in such a gamma space where rho ENS is defined. That means the ensemble points are very densely spaced in the gamma space. Okay. Rho ENS is defined. Now we concentrate on one single member of the row of the ensemble. That means in gamma space we have, this is gamma space, okay, gamma space. Now in this gamma space we have sufficient number of points. Each point, remember, each point again contains 6 n values. Now these points are very, very densely spaced. Now we concentrate on one such point and we trace its evolution with time, only one such point. If we just trace its trajectory in phase space, okay, then we know what rho ENS is, or we can calculate what rho ENS is at every point along the trajectory of this particle. So, the basically the strategy is that first we have to create a dense ensemble, then we define the density of the ensemble rho ENS, then we just concentrate on one single member of the ensemble and we trace its evolution. Now we calculate again the rho ENS at every point of the trajectory of the evolution. Okay. So, if we calculate, do all these things, basically finally Liouville's theorem says that d dt of rho ENS will be equal to 0, okay, where d dt is the time derivative of rho ENS along this trajectory. Okay. What is the proof of that theorem? This is also very interesting. Now, we first take along this trajectory. Let us do this in a elaborate way over here. It is a trajectory, okay, and we have point over here and another point over here. Let us say they are infinitesimally placed, okay. That is not clear from this picture, of course. So, this is the point at t, time instant t, and this is the point at time instant t plus delta t, okay. And their states are given simply by, here the state is given by QSPS. I am just writing in terms of the generalized coordinates and generalized momentum, but for your convenience just let me just tell you that this is nothing but the position, this is nothing but the velocity, for example, okay. And here that will be QS plus delta QS PS plus delta PS, okay. Now you see that here, although I just wrote QS PS, basically every Q says there are 3n number of values for that corresponding to that QS, and for PS is the same. So, 3n plus 3n again 6n values, okay, must be. So, 3n values, and here you have also 3n values, okay. Now, we want to calculate d rho ENS dt, and we simply say that this is nothing but limit delta t tending to 0 rho ENS at QS plus delta QS PS plus delta PS t plus delta t minus rho ENS QS PS t by delta t, okay. Once again, when I am saying all these things, these are actually designating these 3n quantities, these are also 3n quantities, okay. Then you can again write by doing some Taylor type of expansion, you can write rho ENS QS plus del QS PS plus delta PS t plus delta t will now be equal to rho ENS at QS PS T plus summation over S. Now you see why, I mean that is now clear that there are actually 3n, 1 to 3n, okay, delta rho ENS delta QS delta QS, sorry, del QS delta QS plus summation over S 1 to 3n del rho ENS by del PS delta PS plus you will have another term which is del rho ENS del T times delta T. Okay. This is just we can get from Taylor's expansion. Okay. So, we have to calculate now this one. So, if you just take this term to the left hand, I mean left hand side and divide the both sides by delta t and taking the limit that delta t will tend to 0, then basically you can see you will be simply given with this del rho ENS dt will simply then be del rho ENS del t plus summation over S del rho ENS del QS QS dot plus summation over S del rho ENS del PS PS dot, okay, where dots are nothing but the DDTs. So, PS dot is equivalent to, okay, d PS dt and QS dot is dQS dt. Okay. Now, here you see that here you have 3 contributions. Okay. Now, finally, we have to prove this is 0, right. How to do that? Okay. Now, we start by doing a simple thing, that is we will try to discuss or rather we will try to calculate the dynamics of the ensemble points in the gamma space. What will be this? Now, till now we have said that the ensemble points are so densely spaced that you can define a density for the ensemble points, right. Now, if we consider the conservation of ensemble points, okay, let us consider the conservation of ensemble points, of course, in gamma space. Okay. What is the meaning of that? If you just take any arbitrary volume element, let us say arbitrary volume like this, okay, then the rate of change of the number of ensemble points in a test volume V, let us say this is V, okay, will be equal to the flux rate of the particles to the through the boundary surfaces enclosing the volume. Okay. That is something you all know from the basic hydrodynamics, right, that when some fluid is not having any source or sink inside this volume, that means the rate of change of the mass of the fluid inside this, okay, inside this volume will be exactly equal to the flux rate of the particles or flux rate of the fluid through the surfaces. Okay. Okay. So, how to write that? The formal way of writing this is ddt summation integration over rho ENS. Let me just do something like this. Here I just say yeah, okay, this d tau, this is the total time derivative of the mass of the ensemble points. Now again, once again, they are not real particles. So when I talk about mass, this is a representative mass, this is nothing but the density times the volume. Okay. So this is the number, I mean the rate of change of this. So basically what is this? This is the number, okay, this is the total number. So there is a change of the number of the particles from an arbitrary volume in gamma space, that will be equal to minus of closed surface integral rho ens u dot ds. Okay. That is just to say that if this one is, I mean if the change of mass is positive, okay, it should be coming inside, and if the change of the mass is negative, then it should come out of the surface. Okay. So that basically says that these two will be related by a negative sign. Now what is this? By Gauss's divergence theorem, you all know this is nothing but minus volume integral divergence of rho ens u dv or d tau, sorry, d tau. Okay. So finally we have something for rho ensemble, this very I mean okay, then this one will enter in the in this integration as del del t. So finally we will have del del t, since this is a volume element, okay, and space and time they are not, I mean they are not seeing each other. So basically by the Leibniz rule, okay, the differentiation actually can enter inside the integration as a partial differentiation. Okay. So del del t of rho ens will simply be equal to minus of divergence of rho ens u, that is another way of writing is del rho ens del t plus divergence of rho ens u is equal to 0. So that is the equation of continuity for the ensemble points. Okay. Now what is the advantage I get from this equation? Okay. If you now see, there is a lot of advantage, because this divergence term you can now write like this. So del rho, this is the continuity equation, I write it, plus divergence of rho ens u is equal to 0. We call this continuity equation. Now this continuity equation for the ensemble points, okay, continuity equation for ensemble points. Now if we have this, then we can easily say del rho ens del t plus this is nothing but summation over s del qs rho ens qs dot, okay, plus summation over s del rho ens ps dot del ps, and this is equal to 0. Now why is this? Can you understand this point? Okay. That is because u is nothing but, so if you understand what u is, u comes from here. So u is the velocity, of the ensemble points during its evolution. So u is nothing but the gamma space velocity. If the gamma space is of 6n dimension and it just the point coordinates, the point position coordinates are qs ps, okay. So remember ps is also inside the position coordinate, okay. All of them together gives you the 6n dimension, okay. Then the corresponding velocity in gamma space will be just qs dot and ps dot. Dots are nothing but the time derivatives of them, okay, the total time derivative. Now if you have this, then u can be written as qs dot and ps dots, okay. again Qs dot has 3 n values and Ps dot has 3 n values. So, U also has 6 n values, right, if the time is frozen over there. Okay. Now, and why the other things? Because divergence is nothing but the partial differentiation with respect to the position coordinates. Here the position coordinates have 3 n q and 3 n p. So, that will be summation over this plus summation over this, right. That is our divergence here, of course with their unit vectors. That is our divergence. Okay. Now, finally, we have this, and if we have this, then again we can write del rho E n is del t plus, then this can act on both of these quantities and same for this. So, every term del del q s of rho E n is q s dot will give us 2 terms. Okay. So, finally, we will have, if you understand this clearly, we will have del rho E n s del q s times q s dot plus summation over s del rho E n s del p s dot. So, that was the term where del del q s and del del p s they were operating on rho E n s. There will be other terms like plus summation over s rho E n s, and rho that will be actually rho E n s will be the common factor. So, you can easily say del q s dot by del q s plus del p s dot by del p s. That is 0 from your equation of continuity, right. Now, what you also know that this is the definition of your d rho E n s dt. Okay. If you just go through this definition, you will see this is nothing but these terms. Okay. So, then finally, we can write from here d rho E n s dt plus summation over s rho E n s del q s dot del q s plus del p s dot del p s is equal to 0. Okay. Now, we know that we have to show this is equal to 0, this one equal to 0. So, what is the only way of doing that? We have to prove this one is equal to 0, the second term. Okay. So, now remember there is an equation called Hamilton's equation, and as the microscopic systems are all conservative in nature, then basically for every position and for every momentum, okay, you can define a conservative system. I mean, you can write a Hamiltonian of a conservative system, okay, using those, okay, and then finally you can write that for the total Hamiltonian, you can simply write del H del P s is equal to Q s dot and del H del Q s will be equal to minus P s dot. Now, this Hamiltonian is a Hamiltonian for the real particles who is having the real n particles who is having Q s and P s as their coordinates and momenta. Okay. Or I mean, now you do not have to go to momenta, you just say okay, it is something like velocity. Of course, this is okay. Here you just admit this Hamilton's equation. Okay. So, once again what I said that here basically in this total part that these n coordinates are there actually even before that they were the every states were given by r and v. So, this is r and I mean it is a more properly saying it is not r and v, but r and p. Okay, p is the momentum, and then basically using Hamilton's equation will be much more easier. So, Q s will be Q s and P s, the Q s is the generalized velocity, generalized coordinate, and ps is the generalized momentum. Okay. So, by Hamilton's equation we have this, and so we can easily write del q s dot del q s is nothing but del 2 h del q s del p s. This one gives, okay, this, and what this one gives, del p s dot del p s is equal to minus del 2 h by del p s del q s. Okay. As you know that P del p s and del q s for normal state functions, okay, Hamiltonian is a state function, for normal state functions, okay, they are always interchangeable. So, at the end of the day you can say that this is minus of this. So, del 2 del q s dot del q s plus del p s dot del p s is equal to 0. And look, this is 0. So, finally we have, finally we can show d rho E n s dt is equal to 0. Okay. So, this is the proof of Louville's theorem. Now, there is an interesting corollary of the Louville's theorem which says that, let us say that some of the ensemble points which were initially contained in an elementary volume, let us say dV, okay, dV, which you can write now as a product of dqs dps. Now, in time, let us say that was at time t, so at time t prime, which may or may not be infinitesimally apart, this can be after some finite time. Okay. Now, as having the same number of points, okay, once again some of the ensemble points, okay, which were initially contained in an elementary volume dV, now they are contained in dV prime. Okay. So, the number of the particles they are same. So, that means the mass, what I say is the same, d p s prime. Okay. So, we can say rho ensemble of summation over d q s d p s will simply be equal to, so this is summation over, I mean multiplication over s, rho E n s prime is d q s prime d p s prime. Okay. Because the number of the particles are same, the number of the particle is same. Now, Louville's theorem tells us that along the trajectory, if it is measured along the trajectory of one of the ensemble points, not arbitrarily, but along the trajectory of one of the ensemble points, okay, then basically on this trajectory these two will be equal, and if these two will be equal, summation over s, product over s dqs dps is equal to product over s dqs prime dps prime. So, you see that if you are now, for example, if you take some elementary volume, okay, in the phase space where this volume is containing initially some of the QSPS, some of the ensemble points of course, and then you let them evolve and you trace how those same number of those particles, let us say you first take some ensemble points, you color them, okay, so that you always can recognize them. Okay. Then you trace them, and after some time at some later instant t prime, okay, let us say you are now saying that this packet of particles are now having another volume. Okay. Before it was dV, now it is dV prime. Okay. But we have always given the restriction that we are always we are always tracing the number of the particles, or the the collection of the particles, or particles means here the ensemble points, not the real particles, ensemble points along the trajectory of one of the ensemble points. Okay. Then what happens? Then you will see that the elementary volume, okay, which they occupied before and which they occupy now, they are exactly the same. Okay. So, that means that in case of Louville's theorem, we can say that along the trajectory of a real of any of the ensemble points, that means along the trajectory of a real evolution, basically the phase space volume does not change. So, the phase space volume, behaves like an incompressible fluid, okay, incompressible fluid element along the trajectory of an ensemble point. Okay. So, in the next lecture we will be trying to discuss about the classic equation, or the basic equation of the kinetic theory, which is the equation of Boltzmann. Okay. Thank you.